Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Yesterday, Abraham Neyman told me how he first got into game theory. First, he solved his thesis problem, and then he was told it's actually a problem in game theory. So, anyway, let's hear him tell us about learning and competition with finite automata.
Thank you. It's a great pleasure to be here and to talk on this topic. And in particular, you will see that part of the advance has been achieved while I was visiting last time. So part of the advance was during my last visit to Microsoft Research in May. And we'll see, I'll try to pose a problem. We'll see that it's a kind of an epsilon advance towards some goal that maybe, I hope that with the aggregate sophistication of Microsoft Research, maybe at the end of this visit or next visit, somebody will solve the main problem that I'm interested in. So let me start up front by saying that there will be two papers, two results that I'll be talking at this talk with explicitly mentioning the results and maybe saying something about the proof. The first one is the joint paper with Joel that started here last May. And the second one is a kind of a companion paper to that basically serves as part of the first result. It's an older result, but I wasn't thinking of publishing it before I realized that there is also use in one of the problems that was really of interest to me. And a third paper that maybe it's just for an advertising. It's a graduate student in Jerusalem who has done related work on the strategic value of recall. Yes, and the general topic is how we could view learning and competition with finite automata or finite memory. I would make later connection between the finite automata literature and the finite learning literature. And so just that you have a glance of some of the papers that are related, and I would maybe just mention here and there something from these older papers, but I'll focus on the previous papers. And few other contributions to the general area of these literatures include Bavli, Gosner, Hernandez, Lehrer, Papadimitriou, and Akakis, and probably many others that I'm not familiar with their work. So the outline of the talk, as I say, there will be two main topics. So the first one, which is the title also of the paper with Joel, is complexity and effective prediction. And we will have the first posing the question, then posing the solution, and then stating the open problem, which was basically still open and motivated this work. Then there is the other paper on the strategic value of memory. We will pose the question, we'll pose the solution, and then we will ask questions about the learning duration. And I'll pose the question, I'll pose the partial answer, I'll pose the open problem. I think it's a problem that again, during the last visit, few people here were interested, or we tried to see what we could do. And then if I have time, I'll say something about learning with bounded recall. But that's more usually you put the outline to indicate what you are not going to talk in. So I don't think we'll get to this other problem. So what is the question? So consider a two-person zero-sum game. A repeated two-person zero-sum game. So if you want, you could view always or think of many of the questions related to the famous matching penny game. So there are two players that simultaneously, player 2 has to guess the outcome or to misguess the outcome of player 1, and player 1 who chooses the rows and player 2 chooses the column. They do it simultaneously, and if player 1 matched the action of player 2, he gets 2, and otherwise he gets 0. So the objective, we think of it as a two-person zero sum, namely the payoff that appears here is the payoff that player 2 is making to player 1. So player 2 is trying to minimize that number in this matrix. So the question is, how much smarter must the player be to effectively predict the moves of the other player? So we look on this game as a repeated game. So if player 2 would know, they act simultaneously, but if player 2 would know the action of player 1, so if he knows that player 1 is going to take this action, he would like to take this action, to pay just 0, and if this action, he likes to play the other action. So the question is, how much smarter must the player be to be able to react in such a way? So the answer obviously depends on what do we mean by the meaning of effective prediction. So I explained essentially what is effective prediction, but what I would eventually want to say that effective prediction, I don't care if I miss here and there, but I want that most of the time, in most of the stages, I'll be correct in my guesses. So I allow small, negligible mistakes. Obviously, the other aspect of the answer is how do we measure the smartness of a player? So what is the measure of smartness that we have here? And then we would realize that the answer depends also on, that's the conceptual aspect, and then there would be a technical answer that it will depend on how many actions in the stage games do we have. So in this case, it is just a 2x2 game, but it might be a function of how many. For instance, if player 1 has just one action, then it's very easy to guess what he's going to do. And if he has more, then maybe you need more resources, you need to be more smarter in order to always be able to guess.
So what is the setup? Should I think of one of the players being a polynomial type program? And if so, is that program published or not?
First of all, I say that it depends on those things. And I haven't yet explained the measure of smartness, and this is soon to come. And what I want to talk about the smartness here, so if the question already came at this stage, is the size of the memory that a player has. Okay? Or more explicitly, the size of the automata that the player is playing a strategy. So,
you're not allowed randomization.
and I don't allow randomization, yes. So I think of a creature that is basically an agent, so a bank teller, is not going to flip a coin each time that somebody is coming in front of him. And, but the program that, by which he's taking actions, and many firms do act like that, the instructions are deterministic. The fact that you don't know the program that is giving this deterministic instruction, this generates the randomness. So I want to think of deterministic agents, but the program by which they are acting is unknown. And we want to break the code. Simple enough so a bank teller can understand.
So it could be like in a, like if you're playing blackjack in a casino, the guy who's playing with you for the casino knows what he's supposed to do, knows whether to get hit or not.
Yes, but he is a random machine. Yes, so
Right.
But if you think of you know, some people told me, I never made these experiments, that they teach random numbers or encryption in business schools. And they have the students all with the most recent model of a computer, and they told them, pick a random number, yes, and many will pick the same number. Yes, so there is, you know that the machine is somehow bounded. Yes, there is some finite number of states in the machine, so you don't know the program by which it is being generated, but you want to use the fact that it's bounded. By the way, another story I heard, and I haven't, sorry?
You know the bound. So I go to the bank teller, and I'm sort of the thief who really wants to outsmart him. Do I know that he has memory of 10 bits?
You know that he has a memory of some size. You don't know if exactly if it's 10 or if it's 20, but you know the order of magnitude. You know the person, you know his order of magnitude. By the way, another story that I heard, but I've never been able to confirm, is that the reaction for audience to this type of talk is that it looks a very silly game, right, to play if you could flip a coin and so on. A similar game is Evan Yahumis Prime. What's the
Rock, paper, scissors.
Oh, yeah.
Rock, paper, scissors. And I heard that there is the world championship in that, on repeated playing. And the rule is...
a front page article in the Wall Street Journal
Yes.
on the rock, paper, scissors championship.
Yes. So they have a championship, so I see it's the two stories too. And indeed, some players try to outguess the output of the others, and some are consistently successful.
Yeah.
Another example of outguessing players in such simple games, which again I haven't looked exactly on the machine or the output of the experiment, was that Shannon was constructing a machine to play matching pennies with visitors. I think at that time he was a trend, and he was beating with a very simple machine most people on matching pennies. Okay, so people.
This is matching pennies.
This is matching pennies. Okay, so you could say if you really could flip a coin many times one after the other, there is no way whatsoever that another player will be able to guess it. But usually when you play matching pennies, even as small kids, I remember I would play and you try to guess what is the kind of algorithm that the other player is fitting head and tail. So first of all, this concept of effective prediction that I already said, effective prediction means that no matter what the stage game payoff function, the player can play with high probability the best reply in most stages. So against this, the best reply for player 2 is to take this column, and against this is to play in this column. And I don't care about few mistakes here and there. And the smartness is measured in all the papers that I would speak about the size of the automata that implements the strategies. So what is an automata? In a moment we'll have the formal definition, but it's a machine with finitely many states. Each state represents a state of memory. And as a function of the state of memory, you decide which actions you take. And as a function of the input, namely the action in the previous round of the other player, you move to another state. Okay? So just a short connection with some work in statistics. I think initially finite memory by Robbins, he modeled it with finite recall. And thereafter, I think people shifted into working with finite memory as finite automata, and this was initiated, I think, by Cover, who re-examined work of Robbins in this setup with finite state machines, which are called automata. Yes?
So one small question. So when you say prediction means predict the best reply in most stages, I mean, do you mean
in most stages,
more than half, or really 90%?
No, most, nice percentage. Effective prediction will be in 99.9% of the rounds.
But even 60% would seem like a useful thing to be able to do, right?
Very good, very good. We'll come to the open problems later, okay? I don't know how much smarter you have to be in order to guess 60%. I know how much smarter you have to be in order to guess 99.9%. And that's exactly a question that will come later. Okay? So let's just make sure that we follow what is the finite state machine, the finite deterministic automata. So an automata of player 2 contains a set of states. These are the states of memory of the machine. And it contains the action functions. So as a function of the state, which column does the player take, left or right? And it contains also the transition that in a given round, if it was in a given state and the action of the other player was I, what is the new state that the machine is moving to? And obviously, we have to initiate the machine, so we have a starting point. So the program that we put on a machine, which will be the random variable, which will be the possible mixed strategies of the player in this repeated game, would be these entries, the function alpha, the function beta in the initial state. Okay? The size of the machine will be something. The size is the number of states. Obviously, with You could take different states, but it doesn't matter in terms of what are the strategies you could implement.
Well, that means I don't know the order of magnitude, because if you tell me that, because, for example, if the size was 500, maybe I choose rules which stay within 2 states. So
yes, but you will see that the results will be
wouldn't want to do that.
An upper bound.
yes, it will be a function of an upper bound. Okay, so you know that it's less than 1,000. You don't know, and then you could ask yourself what is the size. You don't necessarily have to use all the machines, but by knowing M, you know an upper bound. So.
We've certainly met students who don't use.
So what is the strategy if you have one such program that you program the machine? So it defines a strategy. A strategy in a repeated game is a rule that specifies which action to take at every round as a function of all the observables from the past. So one model is the standard signaling, which is after every round of the game, the players observed all the moves of all the other players. There are some other games by which some player doesn't observe the move. The payoff accumulates, and only at the very end you know what was your score in the game. But for the first part of the talk, I want to think of a situation where the players observe the moves of the other players. So the strategy of a player of such an automata, it's, first of all, we define the sequence of states of the machine. We start with M1 is the initial state of the machine. And the state in the next round is a function of the state of the present round and the action of the other player in the first round, that's the new input, and the function beta. Obviously, I could have put here also a function of J, the action of this player himself, but this is specified by the action function alpha, and therefore I don't have to specify it here. And what's important to realize is that empty, at least for the formality, is a function of the history up to the game. You tell me the history, I could compute empty, and therefore I could define the action tau as a function of the history, which is the action which is alpha of the present state empty. And now I'm going to examine the following game. It's a game G of 2 parameters, K and N. And Joel likes to state it as follows, so I'll use his words before I write the formalities, is each player in his turn has to give to the referee a finite state automata. Player 1, an automata with size K, player 2, an automata with size M. And then the 2 automata interact with each other. Now, obviously, if you look on the 2 automatas starting to interact, the number of pairs of state of machine number 1 and state of machine number 2 is finite. It's the product of K times M. So after a finite number of times, there are 2 pairs of states that repeated, and therefore the game enters essentially into a cycle. And you could define the payoff, the average payoff per stage. So the possible strategies of player 1 are those. So this game is these automata, so it's like saying that those are all the strategies that are defined by an automata of size K. And the possible strategies of player 2 are all those machines that are, all those strategies defined by automata of size N. And the payoff is the average payoff per stage. So we say that 2 such machines enter into a cycle. So we could talk about the average payoff per stage. Now, this is a 2-person zero-sum game because every player has a finite number of strategies. The number of machines that you could write with M states is finite. The number of strategies, the machines maybe is infinite because you could take different sets. But the strategies, it's a finite set. You could have even. So you have a bigger, so this game as a function of K and M generates a very big matrix game. It has a value. And what we want to study is what we could say about the value of this as a function. The max min. The von Neumann value of the game. The max min, where every game has a max min. It's a payoff that player 1, by playing a mixture, a lottery over his pure strategy, could guarantee that no matter what the other one is doing, he will get at least his payoff. And player 2 has a strategy that a mixed strategy over a strategy that by playing that, no matter what the other player is doing, the expected payoff is going to be no more than this value. So every.
But you're not allowed to use randomization.
The randomization is the program that I put on the machine. So
You're picking the automata.
You're picking the automata. The automata is deterministic, but by you picking the automata, you could put various programs, and I don't know which program you put. I'm trying to...
Automaton is a pure strategy.
So what is written in the matrix in entry ij is the payoff of running automaton I with automaton j.
Correct, yes.
But the automaton I could actually be a mixture of...
No.
No, the automata itself, once they play, it's a deterministic machine. But the fact that I don't know which automata is being chosen by the opponent makes the element of randomization, of uncertainty that I want to learn.
Why is it a zero sum?
Because the payoff that
One gives it to the other.
Whatever player 1 gains is whatever player 2 loses. Yes. Now, let me tell you up front that obviously as game theorists usually we are interested in non-zero, not necessarily zero-sum games, but the zero-sum games are the building blocks to analyze the non-zero-sum games. And if you study repeated games, then there is a kind of a folktium that basically tells you that to solve the non-zero-sum repeated game, you have to solve two different two-person zero-sum games, and their solution together with the matrix games enable to you to characterize all the payoff in equilibrium. So that's an important building block of the general theory, but let us focus here just on learning and competition. So when I say competition, I mean the two-person zero-sum game. And now, if the player would have been able to outguess at every round the move of the other player, then player 2 will be able to bring for every I to choose the j that minimizes the payoff of this matrix, the gij. So I and j are the actions in the one-stage game. And let's remember this number, which is the max min in pure strategies. Yes?
The game that is repeated is the game of the two deterministic automatons. It's not the...
No. It's a one-stage game, like the matching pennies, that is being repeated over and over.
But you don't repeat the randomized game of the
No.
strategy. Okay.
Yeah.
So you repeat it.
What is little g of I and j?
That's the payoff. That is written here. This is the set I.
Payoff in the pure game.
I and j is now in the super big space of all possible machines.
No.
It's building blocks.
In the stage game.
Oh, this is I and j have just two elements.
Yes.
In this example.
So in this example, it's two elements. I is either top or bottom. J is
Rock,
left or
paper,
right.
scissors, it's three,
But it could be a more general matrix as well. So the question is, what is the asymptotic relation between K and N so that whatever the stage game payoff G is, so put here other payoffs, here I gave an example 2 and 2 and 0, 0, it could be 4 and 2, it could be anything else. So what is the relation between K and N so that whatever the stage payoff is, the value of this game with the automatas would be this V star of G, which means that each time I could guess indeed correctly to bring him to the minimum. Obviously, if you look on this quantity, player 1 could easily guarantee that with a single state machine. Okay? If you pick the I that is maximizing this expression, he could repeatedly play this action. Okay? So there is no chance of bringing him down below that if player 1 is smart, even if he's quite dull in terms of states of machines, if he has just one state. So the optimal that we could hope in this game is to bring down to V star of G. So what is the answer? So maybe let me pause in a minute and let me wait for suggestion, at least for that game. So player 1 plays with
Maybe
K.
I misunderstood you, but I thought you just replaced us as the block destroyed.
Yes, why?
Well, you don't say I can just with one state of memory do.
It's a bound.
What does the other place?
That's a bound. So with one memory, player 1 could guarantee V star of G. But my question is, what should be N? How big should be N? How much smarter should N be compared to K? So that the value of this new game with the machines will come down to this V star of G.
So
in
V
this
star
case
of
to
G is
0.
0 in this example.
So in this game, how big should be N such that the value of the game between the machines will be such that the payoff will be 0? So any idea what?
Exponential. Exponential.
Should be exponential. How exponential? So the answer is, it depends obviously on the number of actions. So here in this example, I and J is equal to 2. So it's like N should be at least 2 to the power k in the exponential scale. And I'll elaborate and explain what does it mean in the exponential scale. So the explicit condition is that if we look on a sequence of such games, so we have k goes to infinity, we'll think of player 1 smart, so k is very large, and n is a function of k, so nk. If the log of nk, if the lim inf is at least this minimum, so in this case it's 2, then the topper, the answer on the top will be obtained. So I think it's relatively easy, yes, and this I knew for a long time, that if n equals 2 to the power 1.1 k, so if it is more than 2 to the power k, which is this expression, then it was not completely trivial, but not difficult to prove that for this case, yes, for this case, the value is 0. Okay? It is almost trivial if it was k to the power k. Okay? If the size was k to the power k, then it's almost k to the power 2k, just to be on the safe side. Some constant here. Then if it's that size, it's almost trivial that the smarter player could outguess the first player. Here it's a little more...
How many possible
and
strategies?
this answer basically says that also if you have 2 to the power 0.9k or 99k, then you get very close to 0. Yes. When k is very large, so there is no phase transition at 2 to the power k. Yes. Initially I was... I made some conjecture later, I'll tell you, which I was careful essentially about this point, 1. Yes, and I'll explain later exactly what is the conjecture. And I was suspicious that there might be some phase transition in one single point in the exponent. And I haven't wrote it explicitly, but I was afraid about the 2 to the power k. And the answer is here that it's not.
Let me ask a question.
Yes.
If player 1 has size k, how many machines are there of size k?
K, about k to the power constant of k.
And that's, so after that time I can sort of figure out what the other machine is. Would just...
You are now asking a question that was part 3. How long it takes to learn. Okay? How long it takes to
I
take.
see, I can actually run.
So there is a question here. The game repeats itself infinitely many times. Okay? There is no issue of the duration yet. Okay? Part 3, there will be exactly this issue, how long it takes to learn. Okay? And but essentially, if you take something of this order, you could build a machine, a deterministic machine, that will basically check one after the other of the other machines, and basically will get to learn. With this size, with 2 to the power 1.1k, there is no way that you could check all the machines. You don't have enough states. But there is a way to win the game, to bring him down to 0.
And what is it?
Well,
In a moment.
Here.
At the very end, we'll get to the proofs. But so, first of all, let me make sure that we understood the condition. So first of all, it has 2 parts. Since I said what is the condition, and I say this is the condition, so the condition is sufficient. It means if the limit of the log of the other one divided by k is at least this, then the value converges to this v star of k. And the condition is necessary, and this means that if the lim inf of that is less, then there is a stage game payoff, because we wanted for every stage game payoff, there is a stage game payoff. Obviously, if the game is all 1 or all constant, there is no game to play, because, for instance, this game. So there is a stage game payoff G such that the lim sup of the value is more than v star of G. So for a sufficiently long game, player 1 could protect something more than this v star of G.
And you really need this all lim inf sup? I mean,
What?
it's not, you really need all this lim inf and lim sup? I mean, it's not true for
No,
fixed...
no, I could say if the limit is less, it's the same thing almost. Okay, it just since I run on k and not a subsequence of k, So to be formal, you have to write the lim sup and the lim int and so on. But it is true that if the limit is less than, sorry. Very good question. Again, it relates to the open problem that I don't know the answer. If this limit is a number that is less than that, between 0 and that number, I don't know that the limit of these values converge. So for instance, if you look on this particular game, let me pause right here the game. If n equals 2 to the power k over 2, you could look on the value of these games. I have no idea if it converges. I guess that it converges, and I guess that there would be a nice formula for the limit, but I don't know the formula, and I don't know that it converges.
I didn't understand something. So you said that the 2 to the k is not a transition point, but according to this slide, then it is a transition point.
Not a phase transition.
No, not a phase transition. It means when you are slightly below, the limit will be you will get a little below, but very close to. So for every epsilon, there is delta, such that...
It is a transition point, okay, of the derivative.
It's not the first order, isn't it? It's the second.
I don't know about the derivative. If it's
No, what I'm
positive
saying
or...
is that it's...
No, but
Oh, no, I know,
First
sorry, I
order
know
phase
about the derivative.
transitions
I know something.
Right, first order phase transitions are the things that jump. And what these guys are saying is that possibly it could be a second order phase transition.
I'm
Yes.
not sure that that's a
I don't know.
Um,
I don't know. I'm not sure what the order of it is.
so if, maybe let me draw here this graph.
It would be fair on
So here we think of k large, and here we think of log m over k. Okay, so in this particular game, so when this is 1, then it is 0. The graph says that this is 0, and basically for more than 1 it is 0. And when it is 0, when log n over k, when n is sub-exponential, but still n, so n, let's always assume that n is the smarter player. So if this is equal to 0, then this is equal, player 1 could protect the value of the game. So here it is, the value of this game is 1. Okay, and I know that for every epsilon larger than 0, there exists delta such that the value of the corresponding game for sufficiently large games will be here when n will be in this box. So it's close to this limit point.
So that
I
looks...
never know a lower bounds. It could be 0 all the time.
No, I know that there is no lower bound where it is 0. For this particular game, it is strictly
really
above.
does look like a
It means
second order phase transition.
I can draw. I don't remember the shape, so because I don't remember the shape, I'll draw it a straight line. But it's not a straight line. It's a straight line after rescaling this interval, and I don't remember if it's convex or concave. I could compute it. In a moment we'll get the formula. That the value is always above that line. Okay? So there is here some strictly monotonic curve such that the value of the gain for the relations of log n and k is strictly above that line. Okay?
Found in the other defaults of one where it's strictly below. You know one where it's strictly below? Except for the square.
And it jumps to 0.
Essentially here.
Then it jumps to
But I know that it doesn't jump. Yes? So here there will be some other curve. Okay? I haven't tried to compute it. So more or less maybe some other curve like that I know that it's in between those two functions. I don't know anything more than that.
So you don't know what are the derivative of these bounding curves at 1?
This one I know. This curve I know.
Derivative at the bottom.
At the bottom,
Do you know there is a derivative which is free?
no, but I could recompute it from the proof. So that's something, but it might be infinite. Okay, so you have to be careful, but computable from the proof.
So you do know how it goes up exactly, not only.
No, I don't know how it goes up. I know that the proof gives something about this. So the proof gives something, but I don't know that this is the right bound. So there will be this function I know, and this will be in the second part of the.
So the proof gives.
Proof. So the formula for this function I can write.
So you have a constant lower bound on the derivative.
Yes.
But the upper bound may be infinite or not.
Okay, so let us just recall what we have already discussed, which is the max min, of this game. So the value of that game is the maximum over all. So if sigma k are all automata with k states, so delta is a mixture over that. So we player 1 picks a mixture of that, and it implies that for every distribution over delta sigma k, there exists some machine of size delta k, that the payoff, the average payoff per stage when those two machines interact is the value of the game. And the second part says that there exists some mixed machine of player 2, so he could conceal the machine such that for every, he could take a lottery over his automata with nk states, such that for every machine with k states, the payoff will be this value of the game. Yeah, so that's the minimum. And okay, so and now the open problem, which I already stated it here as a sample when n equals 2 to the power k over 2. So quantify the level of prediction. So here we had full prediction, effective prediction. We predict exactly. But maybe if it's 2 to the power k over 2, maybe I could half of the time predict correctly and the other half to be average. So I'll get here a pair of 3/4. So maybe other relations. So if the log of nk over k converges to theta, and theta is some number between those two bounds that from this picture I know how to solve, does the values of this game converge as k goes to infinity and this goes to theta?
Or maybe at least is the lim sub bounded away from 50%.
Again?
Or at least is the lim inf bounded away from 50%. Can you at least do 60?
Yes.
Which is a weaker.
Sure, which is a weaker conjecture. So that's an old conjecture of mine, and at the time when I conjectured it, I say, I conjectured this is true for all but possible one value of theta. And if I left to conjecture now, I would say true for all theta because I was considering a possible problem at the k equals 1, but
why do you believe that the limit exists and there's not some examples where you may have a lim sub? I mean,
mathematical beauty, I would say. Okay? And so far all advances have showed that this is happening, but we'll see in a moment what happens in a slightly modified setup that indeed this
but there's sort of ugly stuff in Nash equilibria and stuff. So
it's even 2 per zero sum. Yes, it's if you are bounded. I think if you are bounded with your resources, there is some limit, some way. There should be some way that will tell. So how much could you learn about it? Okay? And we'll see a modified problem. Okay. So and for those value, what is the value of this game? And as I say, just the left-hand side there. Is an old work of Ben Porat. It was his master's thesis to prove that if the log of nk over k is going to 0, namely we are at the left-hand side there, then the value of this game goes to the value of the stage game. So basically, in order to have some advantage, you have to be polynomial. If you are sub-polynomial, if the smarter player is sub-polynomial, you can do nothing.
You have to be exponential.
You have to be exponential.
Sorry, exponential. Yes. If it's sub-exponential, no good. No advantage. Okay. So yes.
Just one more question. I mean, there are two variants of this problem. One is that if And if the second player the player one choose first the machine, and then the second player, given that he knows what he has chosen.
No, if you know the machine of the other player, then you need just k states to beat him completely, because you just write, you duplicate his machine. He has k states, write also k states, and for each state, write the best reply to the action of the other state of the machine, and make the transitions the same, imitate the transitions of the other player. So if you know the machine, you need just k states.
But it could be also the other way. Say if k knows n, if n chooses first the machine, and k is still smaller, if k is log n, or n is 2 to the k, as you described.
Okay.
So say you know.
Very good. So let me answer this in where I know and where I don't know. Okay. So in the statement of this, you see that the value is the max mean, the min max, and the mean is over mixed strategies. Okay. Now, if n would be that size, or some constant here, I have to compute the constant for that particular game, then I don't need to mix over tk. There is one single machine that beats all automata of the other player with size k.
Then you can announce it.
And then you can announce it. You could tell it the other guy if this is the size. I don't know. I don't know the answer.
That's true.
Sorry?
He said you wouldn't be able to read the announcement.
Yeah, right.
So.
No, but the other is allowed to have a big brother who helps him at the beginning of the game.
Yes, who helps him to write his own program. Yes. So it's like God generates the creature. So you know there is a famous, I think, there is a famous quote from a book which says that the U.S. Army, the strategy of the U.S. Army is designed by geniuses to be run by idiots.
Yeah.
And the meaning is not really that they are idiots and these are geniuses. In the design, you could apply a lot of resources. When a company makes the decision of how to implement the strategy and so on, they take advisors, they run computers, they make a lot of computation, and then they have to write a program for the people to run the strategy. And this has to be a simple one, easily implemented. So the design, it's a different layer. So this type of work is not speaking about the design, it's speaking about the resources of memory needed to implement something. So going back to your question, so if I know n, if n is equal to 2 to the power 1.1k, I don't know the answer. What is the min max, where the min is not over mixed strategies of player 2. So if I will write a strategy and the other one, I don't know the answer. Okay? The solution here that you bring him down is indeed by running a mixed strategy, that you don't know the program I was putting on my machine, that we get. Okay, so we stated the open problem. And how much time do I have?
20 minutes.
30 minutes, okay. So since I cannot solve, I was unable to solve the previous problem. So what you usually do, you pose a simpler problem, hopefully to be of independent interest, and you solve it. So let us try to look on the problem of prediction of oblivious automata. What is an oblivious automata? An oblivious automata is an automata that doesn't see the moves of the other player. So it cannot react to the moves of the other player. So essentially, if you have a machine, an automata with k states, it is a machine that enters eventually a cycle of length less than k, but you don't know when it enters this cycle. Yes, the cycle could be of size k over 2 and so on, so it could have some transient states at the beginning and then enters into a cycle. So you know something about that. And in this case, you could also ask the same type of question. If player 1 is either an uncertain periodic nature, so we know it has a period of less than k and it enters in a short while into this cycle, but we don't know exactly what are the actions of the cycle. We don't have information about the actual cycle. And we want to measure the level of prediction of a larger machine that could encode few of the information. But if it is 2 to the power k over 2, it cannot encode in the states the entire cycle. Yes? Because 2 to the power, the number of sequences is 2 to the power k, and it also can be different cycles, so it cannot encode everything. The question is, okay, you have to give something away. How much can you get prediction in that setup? So I designed a different game. So the brackets have changed. And this is the repeated game where the strategies of player 1 are those that are defined by oblivious automata, these automatas that are non-reactive. And player 2 can play with an automata, could record the information and so on. So the answer here there is a limit, a nice limit. So if the log of the larger machine divided by k, the log of the smaller oblivious machine converges to a theta, then the value converges to some function v of theta. And I could write you an explicit formula for v of theta. In particular, for this game, you can compute it. I think I'll make a mistake if I try to compute it, but it's a simple computation. So the limit is characterized by this stage game. And let me explain to you what is this formula and of v theta. So it is equal a max min. Not surprisingly that in the game theory you enter into a max min, but let's try to see what is it maximum, what is the max over, and what is the min. So it's a max min of the expectation of Q, where Q is a distribution over the pairs of tuples of actions of the players over the I and j. Yes. So what is player 1 maximizing? So it's maximum over one entity and minimum over another entity. So the max is over all marginals of the distribution on the actions of I. Okay? You should realize that the oblivious automata could decide on the marginal, right? If he has k, or at least he could approximate it, because he could play an IID. If he decides this p, he could play a sequence of IID with which x1 up to xk are IID, and then you enter into a cycle. So the marginal, the average distribution of the actions of player 1 is he could player 1 as a control over it. So he will maximize over these marginals. And then player 2 will minimize over all distributions. So if player 1 has fixed this distribution, the marginal on the actions of I, player 2 will minimize over all distributions on the square, which have the following property. The marginal over I is P, and the entropy, can I assume here that everybody knows entropy, or should I write it?
I think we're okay.
We're okay. So the entropy is a function, so it's the negative of the summation of pi log I. It's an information theoretic quantity. So it's the entropy, and that's the simplest way to write it. I could write it in conditional entropy. But the entropy of the marginal on I plus the entropy of the marginal of j minus the entropy of the product is less than or equal than theta. Now, always this term is non-negative. So if theta was 0, it means that this equals the entropy of the marginal equals the entropy of Q. It means that it's a product distribution. And if it's a product distribution and you have chosen P to be the optimal strategy in the stage game, you guarantee that you get. So in particular, the proof of that will give also the proof of the Ben-Poratz result that shows that you need to be super exponential. If you're sub-exponential, even if one player is oblivious, he could protect the value of the game by playing a k-periodic sequence where the first k are IID. So v theta is explicit. I think it's the max min of this expression. And you could have wondered whether if the superpower, or if the smarter player would have played, before I advocated to play with deterministic machines, but maybe to play with a random machine, or maybe to play with a machine that remembers, in addition to the history, remembers also the time. in statistics, there are few results that show a big distinction between machines that have only a finite state of memory and are stationary compared to those that are non-stationary in the sense that their action and transition could depend on time. So here, even if the other machine N would have been, the smarter player would also be able to employ randomization and will have a watch to record the time. So you could tell them that on Sundays you do so, and on Monday you do so, and the various other, or as a function of the day. You don't get any better. So the result remains intact.
That seems one of the things I might want to do with time is sort of double time periods to sort of make up for losses in the last one. Right? There's an exponential scheme of times, but all that
doesn't work.
It doesn't work. The answer here says it doesn't work. So let me do the same exercise as before.
Oh, I can't
so
remember.
What about if the player one can have a counter, have a time?
No, if player one is a counter, then it could protect the value. Yeah. There is no problem. Because you could decide on a given sequence, take one state, just one state of the machine, and take a sequence of actions. Take a lottery of it as an IID, and tell him at date number 1 take this action, date number 2 take this action, and so on. So with one state, if you have a clock, you could randomize completely with the program. So the idea is player one, even when it doesn't have the clock, the other one has a clock. So now let me see how you are alerted or not. Yes?
Did you say that this is explicit? You can easily calculate the max min here?
Yes. Yeah. It's an easy computation. Exercise, compute it for that game. I'll make a mistake, I'm sure, but I always, when I teach classes, I say, okay, this, let me try, I'll make a mistake, but you have to do a homework and do it correctly. So I think Yossi probably remembers. So let me, again, try to check up and say, okay, the value of a game, so we have here a particular game, that's the maximum over all sigma, all mixed strategies of player one, the minimum over all strategies of player two, of the payoff with these two machines, sigma and tau. So that's one side of the min-max theorem. And this is larger than, so this is a universal bound. This is always at least the max of the value function v that is defined on the top, where the theta, the error term, the amount of correlation, is the log of n over k. And the others, and this converges, and this expression converges to v of theta, because this function, you could see that it's continuous. And the other direction of the min-max theorem is that the value of kn is the minimum over all machines of size n, and the maximum over all sigma in sigma k o, the top O is for oblivious of this function g sigma tau, right? Somebody fall asleep here. The value is the max min, and it's equal to the min max, right?
But it's all not randomized.
Yes?
He didn't average here.
Oh, here, to write an inequality, I should have written over a mixture over these machines. So without a mixture, it is only less than or equal. And this already is that quantity which converges to this v of theta. So in this type of model, the learning machine of the smarter player could be deterministic. I could tell you what it is, and you wouldn't be able to fool it. So the minimum is obtained with a pure and not with a... Okay, so let me tell you a few more open problems, one at least. So what is the duration of an effective prediction, or the duration of the prediction? How long does it take the smarter player to effectively predict the moves of the other player? And let's go back to the first model. The two are reactive machines. So obviously we studied that by considering the finitely repeated game. So we put, in addition to the parameters k and n, we put a parameter L on the number of repetition, and we ask how big should be the repetition so that the average payoff per stage will be below a given threshold. So it is easy to see that if 2 is super smart, so n equals infinity, so it is completely unbounded, then if the duration is much more than k log k, then player 2 could effectively predict the moves of player 1. In a sense, there is a constant times k log k times by which the player could make a mistake, and in all the rest he will react explicitly. That's a simple.
This is binary search of the space.
Binary search, but the binary to make it smart. Each time. Yes, you look on all the space of automata. Let me give the proof because you will already sees it. So you look on all the automatas and you see how many of the automatas play at the first round top and how many bottom. Obviously by symmetry it's 50-50, but after every history there is a majority to one of those. So you guess that it's that majority. Each time that you are wrong, you have excluded at least half of the automatas that are left. And by counting the number of automatas, the log of this gives you the number of errors that you could make at most.
And that's your k to the k. That was,
this was the number of automata k to the k, so it's the log of that is the k times k.
But after that, you're left with one automaton.
No,
Yeah.
I mean,
You look at all the
the
time.
number of errors is not the time.
In all times.
It's not the time.
So if you take a large constant times k, so the number of times that you made an error is a little O of that.
You threw out half the automaton.
No, when you're right, you don't go out that.
No, you don't necessarily know the automata, but you are sure to be correct against the automatas. Because you
You
don't.
keep those because you're fine.
Yes, as long as you're fine. So maybe
All you want to do
you
is drop
don't you don't go down to the last automata because maybe there are a group of automatas that against this play they enter into the same cycle.
Yes, yes. So then they're equivalent. Then you
Equivalence against that play.
Yes.
They are not. You might have done something others that they will differentiate. So just bound on the number, and so the value converges to this as this is the condition, and again by mathematical beauty, no evidence at all that this is the right condition. Okay, so if the length of the game is little o of k log k, then the weaker player, the dummy player, could act as if he is a random machine. Yes. And even I don't know the answer if it is 10 times k. Yes, so this is a conjecture. There are some rationale for thinking of this conjecture, but
where is the theorem end and when does the conjecture start?
here is the theorem. If Lk is much larger than k log k, that's true, and it is conjecture that this is that
I think that's also a theorem.
converges to the value of the stage gain G as this and the lim sup when the length of is little o of k log.
Do you know something if you replace log k by some other powers of log k? So what if k times square root of log k over lk goes to infinity?
I say I don't even know if it is just larger than k.
Or even then?
Even that I don't know. That's. And now you could ask the same question about the prediction time of oblivious automata. So the same type. So assume that the log nk over k goes to theta. So it's like this example here, n equals that size. And the question is, what is the condition of Lk? How much? We know what is the limit. The limit is this function v theta that we expressed before. And the question is, what is the condition on Lk so that this converges to v of k? Any guess? So the condition that Lk is much larger than k log k suffices. I don't know if it's necessary. I must confess that on this I haven't spent enough time to say if it's difficult or easy to prove that this is a necessary condition. And I think what's interesting here at least for me so far, when I prove that the LK, that this condition suffices, the most difficult part is what looks initially to be the easy part. And this is to find what is the cycle, what is the length of the cycle. If I would have known the length of the cycle, I don't need the log k. And I am unable with, if you would have 2 to the power 2k memory, you could essentially record the first 2k states of the game and compute the cycle of the game. Compute a cycle. You don't need necessarily to find the cycle. Yes. But if you have k over 2, you cannot record the entire sequence, so you might miss. So it turns out that in this case, I don't know how to do it with a deterministic machine. If you remember before, on the theorem on the infinite game, it was the minimization was with a deterministic machine. To learn the cycle here, I know how to do it effectively or quickly only with a random machine. So I could learn it with probability close to 1. I don't know how to learn it for sure in a short time. And after you learn it, basically, you solve the previous solution for the how you learn, how you bit with a deterministic machine and Oblivious Automata. You do a kind of a learning in parallel. Yes, and but this is more to the proof. So the proofs, I assume that you won't like this late part of the day, but if you're interested, I'll be able to sketch some of it.
We have 2 more minutes. Maybe can you tell us like the basic first thing, like 2 to the 1.1k, why you can...
Oh, that's easy. Okay, the 2 relatively easy.
You're looking.
Yeah. Okay. So n equals 2 to the power 1.1k.
Yeah, and we're just playing that game.
That matching game. So it's going to be a random automata. Okay? And I am going to guess, yes, what is the sequence of play that you will play in the first k stages of the game. So I assume that you play x1, x2, xk. Okay? Now, I'm guessing, I made that guess, all sequences equally likely. So I play y1, y2, yk. I should have written I1 up to ik, but okay. So I guess I play here the best reply to this sequence. Okay? Now, if I was right, namely at each point I managed to play exactly the best reply to your action, if I was right, then your states are going, at each time they got, when they were at the same position, they got the same input. So if you look on the states that appear here, afterwards it should be already a state that appeared before. So you enter a cycle.
I don't, once more.
So assume that you play this sequence in the first m stages. I play this one, and now I am looking on the states of the automata of this guy. So the states were m1, m2, mk, mk plus 1. This is more than the number of states. So there should be 2 that repeats themselves. Okay? Now, these are in one-to-one correspondence to these actions. Okay? So whenever you were, if you were here at M2 and this was maybe also M2, so it means that this thing is the same as this, you have equality, and this is the same as this, because I reacted explicitly correctly. Oh, and then you enter into a cycle. Okay. So I'm trying to guess both the sequence y1 up to yk and the 2 places where you enter the cycle. So what is the probability of my guessing that correctly? This is 2 to the power minus k times 1 over k square. Okay, so times 1 over k square. So with this probability, at least I am correct. Okay.
Why is it not 1 over k? You just need to know.
Because I don't know. Maybe that you already entered here a cycle. Maybe from here you jump here.
Okay.
Okay, so I don't know that this is the place the first time that you return. So you have to guess on those 2 places.
Okay.
Yes, where you come back.
But
So-
then you don't need the 2 to the minus k. But okay.
Okay, so you could save a little, but we are working in the exponential size, so this is O 2 to the power little o of k. That's what's important. So the probability, okay, so I'm trying that. What's the probability that I failed?
1 minus that.
1 minus that. How many such rounds should I try, okay, to catch you? So if I'll have 2 to the power k times k square rounds, I already get positive, very small probability, and if I'll take you some large constant of that.
How do I know that I caught you?
Because I realize that I play here, okay, and every time I see what you acted, and I see if I indeed took the action that gives me a payoff 0. So after every round, I see. Now, the idea is the following. So this requires k states of my machine. The time if I missed at some point, so if at some point when I was in these states, if I missed, I jumped to a new independent trial. Now that's a completely independent program of my computer. So indeed, I could make this multiplication. So the probability will be very small. And so with probability close to 1, I'll catch you into a cycle. And if we already went through that, maybe I'll try to explain.
Now you just have to get rid of the k squared for us, and then we're...
No, okay. No, you're right. This is 2 to the power k a little more. And the question is, so therefore
Oh,
1.
no, well, I know the 1.1.
1.1.
What I'm saying is that to get the much harder result,
The
all
2
you
to
have
the
do
power
is get rid of the-
0.99k.
Right.
Yes?
Right.
How do you get this case? 2 to the power 2 to the power 99k. So the idea here is the following. Okay, I think it. I don't know if I'll do all the calculus, convey to you all the calculus, but just the ingredients. Okay. So you don't try to guess him on k, on all the k, everywhere. If you try to guess everywhere to enter into such a cycle, you probably need something like that. I don't think you could make much savings. So I am going to give away a small fraction. And in return, I am going to expand a little the length of this k. So I'll take k times the blocks by which I'll try to guess you will be k times 1 plus delta. A little more, a little small fraction of delta. Okay? Now, I allow myself to make a few mistakes. But I would like the mistakes to be such that they are spaced away. So I want the number of mistakes that I'll have will be less than delta times k. If it's strictly less than delta times k, it means that in this cycle, there are always 2 states by which I was two states that repeats themselves, yes, on which I am correct, because on the rest I'm there. If they are spaced away, so if I take those of the mistakes, if I decide on their location and I put them around the block of sufficiently large size, then I am sure that in the cycle, even if within the cycle there is a mistake, there are sufficiently many correct other places that will phase it out. And because the derivative of the entropies at 0 and at 1 is infinity, yes, you have enough room here to plug this type of mistakes, and that the number of these possibilities will be sufficiently rich enough. So you have many such. The fact that you have increased it by 2 to the power 1.1k, you increased a little the exponent here. But on the other end, you have many possibilities which are more than this delta, because you take a little of delta and a pk of which to to plug the places where you made the mistakes. And you have many such possibilities. Now, you don't check as before that I want exactly this place. I'm just playing my cycle. And within the cycle, I am counting my score. So I'm playing the tick, I take the score. And if the score is wrong, I go to the next try, and so on. So this is the way how to fix the 2 to the power 0.99.
Thank you.